Hi, I am Darshan M from Department of Computer Science and Engineering, Sri Venkateswara College. In the subject of Digital Design and Computer Organization, we will be discussing a research paper on the topic of Deep Spread Multiplexing. Deep Spread Multiplexing, Enhancing Wireless Communication. This paper proposes a novel deep learning based multiplexing scheme called Deep Spread Multiplexing that can outperform conventional spreading techniques. The authors also investigate training methods to improve the performance of the DNN-based encoder and decoder. Deep spread multiplexing is a communication technique that combines aspects of spread spectrum and multiplexing to improve signal efficiency and robustness in communication systems. It involves spreading the signals across wide frequency band while also using multiple data channels or signals simultaneously. These allow for better signal resilience to interference and noise, as well as more efficient use of available bandwidth. Deep spread multiplexing is commonly used in advanced wireless communication systems like 5G, where multiple users need to share the same frequency bands while minimizing interference and maximizing the throughput. By combining these two approaches, it enhances both security and efficiency of data transmission. Generalization of SCMA. Flexible design. DSM can be applied to systems with any number of data layers and resources, unlike the fixed SCMA design. Improved BER. Simulations show DSM outperforming conventional SCMA and DSCMA in terms of bitrate error. Autoencoder architecture. DSM uses DNN-based encoder and decoder in an autoencoder structure to minimize the mean squared error. Training data sets and noise types. Truncated Gaussian noise. Generating training data with truncated Gaussian noise can improve performance compared to pure Gaussian noise. Corruption level. The optimal corruption level for training data depends on noise environment, with higher levels better for noisier channels. Avoiding overfitting. Dropout was found to be unnecessary as proper training data and stopping criteria prevented overfitting. Utilizing channel information. Channel coefficients. The DNN-based encoder and decoder can be designed to take channel information as additional inputs. Adaptive encoding and decoding. This allows the system to adapt to varying channel conditions, improving performances in fading environments. Optimal corruption level. The training corruption level must be carefully selected to match the channel conditions for best results. Complexity comparisons between MPA and DNN-based decoder. Conventional MPA. Complexity proportional to number of message passing iterations. DNN-based decoders. Complexity scales linearly with number of layers and resources. Conventional message passing algorithm MPA. Decoders are computationally complex, especially for large constellations, with performance dependent on the number of iterations. In contrast, deep neutral network, which is known as DNN based decoders, offer lower complexity after training, enabling faster decoding and better scalability for systems like MIMO. While message passing algorithm MPA is well established and reliable, DNNs adapt better to complex environment but require significant training effort and may face challenges with generalizations across different conditions. Deep neutral network DNN decoders are promising for reducing complexity in modern communication systems. The DNN-based decoders has lower complexity than the conventional MPA detection, making it more practical for real-world implementation. Deep spread multiplexing enhances communication efficiency by combining spread spectrum and multiplexing techniques. Key contributions. Proposed DSM, a generalized multiplexing scheme using DNN-based encoder and decoder outperforming SCMA. Training insights. Investigated effects of noise types, corruption levels and channel information of DNN training. Complexity analysis. Showed DNN-based decoder has lower complexity than conventional MPA detection. It is particularly effective. Deep spread multiplexing is particularly effective in advanced wireless systems like 5G, enabling simultaneous data transmission for multiple users and contributing to more resilient communicating networks. Autoencoder architecture. Encoder design. The encoder is a DNN with multiple fully connected layers, batch, normalization, and ReLU activation. Decoder design. The decoder has a similar DNN structure to reconstruct the original signal from the received data. Constellation comparison. SCMA constellation. SCMA has a limited number of 64 constellation points in a dense cloud-like patterns, whereas DSM constellation has a much larger 4096 constellation points, allowing for better separation and decoding. Performance evaluation. AWGN channel. DSM outperforms SCMA and DSCMA by around 1 dB in AWGN channel BR. Fading channel. DSM performance heavily depends on the corruption levels used in training for fading channels. Complexity. DNN based decoder has lower complexity than conventional MPA detection. Conclusion. Generalized multiplexing proposed DSM as generalization of SCMA with improved BR performance and training insights, investigated noise types, corruption levels, and channel information for DNN training. Practical implementation. DNN based decoder has lower complexity than conventional detection, enabling practical use. Finally, in digital design and computer organization, deep spread multiplexing optimizes resource utilization by allowing multiple data streams to be transmitted over shared channels. This technique enhances data throughput and minimizes interference, contributing to more efficient circuit design and improved overall system performance. As a result, it plays a crucial role in advanced communication technologies and complex computing architecture. Thank you.